So now I would like to just focus a little bit on how the equations of voltage and current can be solved. In order to do so, let's imagine a battery, a resistor, and a capacitor, and a point A. So the method that I use to solve this equation is KVL, Kirchhoff's voltage law. So it simply says that the voltage difference between the point A and A is 0, which means that the voltage of point A is the voltage of point A. So VA plus V0, R, and C at time equals 0. V of A plus V0 plus IR plus, minus IR minus Q over C equals V of A. So the V of A on the both sides of these equations cancel. If equation cancels, and we have V0 minus IR minus Q over C equals 0. Now we differentiate both sides with respect to time. We know that V here is a constant, so the differentiation of these with respect to time is 0. So 0 minus di over dt r minus dq dt of multiplied by c. So we know that dq over dt, or better to say it, just let me just illustrate it a little bit better. dq dt multiplied by 1 over c. This term here is I. The differentiation of q with respect to time is the current. So now we can see that if we want to write it one more time, it's minus di over dt r minus I over c equals 0. So we take this part to the other side of the equation. Minus di over dt multiplied by r equals I over c. So we multiply both sides and divide both sides by dt over r, which means that this part and divide by r. So this equation would be something like di over I equals dt minus dt over rc. So the function and the equation is now ready for integration. So integration of di over I and the integration of minus dt over rc. So this part is ln of absolute value of I, and this part is minus t over rc plus a constant. From now, we would do so. And we know that I is positive, so we can take it out of absolute value. Now we simplify this. I equals e to the minus of rc, and we would just extract this plus and changes it to this form. Now I would like to consider this part as an A. So the equation would be something like I equals A multiplied by e to the power of minus t over RC. This is an important formula. But what is important for us is now is what is this A? How can we calculate this one? To do so, I would like to tell you something about how we can calculate A. In order to calculate A, we have to consider or imagine a circuit like this. V, R, and C. We know that when this circuit is closed, for example, consider that we have a battery, we have a switch here, and we just close it. So electrons would be transferred in this direction, and the direction of the current is like this. It's the positive terminal, and this is the negative terminal. So as the first electron arrives here, it would just let one electron from here escape and goes back to here. So an electron would escape from this terminal of the battery, of the capacitor. And after time goes on, there would be a significant number of just charge here that if we want to add an electron here, these electrons won't let this electron to come to this terminal of the capacitors, and it's not possible for an electron to just escape from this terminal, which means that no more current would just pass through this circuit. So it would be something like this. Time equals 0. Time is more than 0, which means that a little time has passed. And time at infinity, that's so bigger than 0. So what I would like to just focus on here is that at first the capacitor would act as a wire. So this one is important. I would like to just write it in red. At t equals 0, a capacitor would act like as a wire, and at time which is so bigger than 0, a capacitor would act like as a open switch. So this is so important. So here in this function, I would like to calculate A by just using the rule that I've just told you. So let's imagine the circuit here. Here we have a battery, a resistor, and a capacitor. So time equals 0. What we have just told you guys is that the capacitor would act like the wire. So this circuit would be simplified to something like this. And from the very basic formulas of the current, we know that the initial current is V over R. So the formula that we have written is that I equals A to the power multiplied by E to the power of minus T over RC. So what if just we give t equals 0? Then we would find out that I equals initial to the power of 0. We know that e to the power of 0 is 1. So I initial is a. Oh, what a coincidence. These two are equal. So I initial equals V over R equals A. So the formula that I would like to just write it in red or purple, doesn't matter. I equals V of the battery over R, which is the initial value of the current, multiplied by the e to the power of minus t over RC. So from this formula, we can easily obtain the voltage over a resistor just by multiplying this equation by an R. So the voltage of the resistor is IR. We know that I is V over R e to the power of minus t over RC multiplied by an R. So these R's cancel out, and we will find out that V of resistor is V of the battery, which is V0, multiplied by e to the power of minus t over RC. And this line is also important because we have the formula for the voltage across a resistor. Now, in a simple circuit like this, we know that the voltage of the battery, if it's an ideal battery, which means that it doesn't have any kind of resistance, is the voltage drop across the voltage of the resistor plus the voltage of the capacitor. So easily we can obtain that V0 minus VR equals VC. In order to calculate the voltage across the capacitor with respect to time, we can easily input V0. Actually, that's also important, so I would like to write it in a different color. Just take green. So V0 minus, we can just input this formula, V0 to the power, multiplied by e to the power of minus t over RC. VC. It can be simplified to V0 multiplied by 1 minus e to the power of minus t over RC. This is the formula of the voltage across a capacitor with respect to time. So at this point, I would like to just introduce time constant, tau, multiplied by C, and the unit, SI unit, is seconds, which means that O multiplied by farad is seconds. In order to calculate what percentage of the capacitor is charged with the passage of time. So, for example, consider that one time constant is passed. So at t equals 0, V of the capacitor is 0. First. Also, let's write the formula for the voltage of the capacitor. This is the formula. And I would like to calculate the voltage after one time constant. So it would be which is, for example, V initial voltage 1 minus, which is just let us to leave it like this, and we have something to show after that. The term here, I would like to calculate the percentage of the the voltage across the capacitor after one-time constant, the ratio of this amount to the V0. So the ratio would be V0 over multiplied by 1 minus 1 over E over V0 multiplied by 100. So these two are gone, and this gives us that this is approximately. So after one-time constant, an amount of 63.2% of the maximum voltage is across the capacitor. And with time, it actually goes higher, but the rate of change is different. So let's see that how much of the voltage is across the capacitor after two time constants. So at T equals 2RC. The voltage of the capacitor is V0, 1 minus e to the 2 minus 2RC over RC. So, which means this is again, we would calculate the ratio . So this would give us 86.4%. So we can see that on the first time constant, the voltage reaches to 63.2% of the maximum, and after the two time constant, it would reach 86.4. And now I would like to give you guys a table for the voltage. We are going to use these numbers in a calculation, and we are going to have an experiment to show you guys how accurate these numbers are. So be sure to watch the next section too. Thank you guys. So guys, this is our experiment. Here we have 5 capacitors, and because we didn't have the appropriate and adequate capacitors, so we have just connected them in parallel. And due to what we have just told you, these capacitance are summed up, and we have the correct and suitable capacitor. So now we would like to just measure the total capacitance of the circuit. And that's 550 microfarads. Now we would like to measure the resistance, and in this circuit we have only one resistance, which is here. And that's 4.59 kilo ohms. And now we would like to connect the circuit to the power of 5 volts, and we want to see how the voltage changes across the capacitors. You have to be careful about the negative and positive terminals. That's fine. So now we would connect the circuit to the power, backlight. And now we would like to show you guys the discharging. And that's all about the basic RC circuits principles. So, as we have shown you guys, we have some numbers and measurements in our previous video, and these numbers are for the capacitance of the capacitor C equals 550 microfarads, and the total resistance, the resistance that we have used, is 4.59 kilo ohms. So, as I've told you, the time constant is R times C. So, if we multiply this number, which is farad, multiplied by 4.59 multiplied by 10 to the power of 3 times, ohms, equals 2.524 seconds, which is our time constant. So, now we expect that after one time constant, 63.2% of maximum voltage is charged, which means that by a simple ratio, 63.2 over 100 equals the voltage of 1 RC over 5 volts. Therefore, V of 1 RC or 1 time constant is 3.16 volts. So, after 2 time constants with the same method, it's 4.32 volts, and 3 time constants, it's 4.75 volts, and after 4 time constant, it's 5.91, and after 5 time constants we can approximately consider it as 5 volts. So thank you guys for watching. So be sure to just like the video and subscribe, and we'll be so glad to know your comments. So be sure to tell us your comments below, and thanks for watching.